What if light wasn't just a straight beam, but could twist, spiral, and carry hidden structures like a coded message from the universe itself? Today, you'll see how scientists are learning to twist light into shapes we've never seen before, and why this might change the way we think about reality itself. Chapter 1. The familiar light we thought we knew. When you think of light, you probably imagine something straightforward: sunlight spilling into a room, a flashlight cutting through the dark, or the steady red glow of a traffic signal. We've been surrounded by light our entire lives. It feels familiar, predictable, even ordinary. For most of us, light is just their tool for vision, warmth, or technology. Science tells us that light is both a wave and a particle, a duality that already sounds strange enough. But even with this knowledge, the image in our minds is usually simple. Light travels in straight lines, bouncing or bending when it meets glass, water, or a mirror. For centuries, this view was good enough. We built our entire understanding of optics on it. We learned how to bend light into lenses, how to split it into colors with a prism, and how to harness it in lasers. The rules seemed solid. The behavior was well understood. But here's the thing. The universe doesn't stop surprising us just because we think we understand it. Over the past few decades, scientists have been uncovering new ways light can behave, ways that break the picture most of us have in our heads. Light, it turns out, doesn't always travel as a straight beam. It can be structured, shaped, even twisted into spirals, carrying hidden complexity in every turn. Think of it like this. Imagine a river. You've seen rivers flow straight. You've seen them bend. But what if the water could twist into a corkscrew as it moved forward? That's what twisted light is like: a beam of energy, spiraling through space, carrying not just brightness, but a unique kind of momentum and structure. This idea is not just a curiosity for scientists. It challenges something deeper: our sense of what light really is. If the light we thought we knew can take forms we never imagined, what else might be hiding in plain sight? Could there be properties of light that nature uses all the time, but we've only just learned to see? Our understanding of reality depends heavily on how we understand light. After all, almost everything we know about the universe, stars, galaxies, even the fabric of space itself, comes to us through light. If our picture of light is incomplete, then so is our picture of the cosmos. This is where the journey begins. From the familiar sunlight that warms your face to the strange, spiraling beams in high-tech laboratories, light is about to show us another side of itself, one that's hidden, complex, and possibly far more important than we ever realized. The question is, once you've seen light in this new way, can you ever go back to seeing it as ordinary? Chapter 2. The birth of twisted light. The story of twisted light begins in laboratories where scientists work with lasers, not just to shine them, but to shape them. Most people see a laser as a narrow, straight beam, perfectly focused, perfectly direct. But in the hands of optical physicists, a laser can become something much stranger. In the 1990s, researchers discovered that they could create a special kind of beam where the light waves spiral as they move forward. This wasn't just a visual trick, it was a new property of light. They called it orbital angular momentum, or OAM. That's a technical way of saying the beam was carrying a kind of twist in its structure. To imagine it, think of a screw moving into wood. It moves forward, but it also spins around its own axis. Twisted light works the same way. It moves through space, but its wavefront rotates in a corkscrew shape. This gives the beam unique characteristics that normal light simply doesn't have. At first, the discovery was a niche topic in physics. It was fascinating, yes, but its uses weren't obvious. Then scientists realized that this twist could be controlled with incredible precision. By adjusting the twist, they could encode information in the light beam, almost like giving it a hidden language. This was a breakthrough. Suddenly, twisted light wasn't just a curiosity, it became a tool. It could carry far more data than traditional light, making it a candidate for next-generation communication systems. It could also be used to manipulate tiny objects, like microscopic gears or biological cells, with nothing but light. Creating twisted light isn't magic, it's engineering. Scientists use devices called spatial light modulators, or specially designed lenses to alter the shape of the light wave. These tools bend and twist the light in precise patterns, giving it the spiral structure that defines OAM. Once you know what to look for, the difference is clear. Shine twisted light onto a surface, and you'll see a donut-shaped pattern, a dark spot in the center where the beam's spiral structure leaves no light. It's not just beautiful, it's a signature of something deeper. But here's where the mystery deepens. If we can make twisted light here in a lab, is it possible that nature has been making it all along? Could starlight, black holes, or other cosmic events be twisting light in ways we've never detected? If so, then every telescope in history might have been missing part of the story. The discovery of twisted light wasn't the end of the journey, it was the beginning. It gave us a new tool, a new perspective, and a new reason to look closer at something we thought we understood. In the next chapter, we'll see why this twist matters so much, and why it could change not only our technology, but our understanding of the universe itself. Chapter 3. Why twisting light matters on the surface. Twisted light might sound like a neat physics trick, interesting, but far from everyday life. The truth is, its potential reaches into some of the most advanced areas of science and technology. One of the most promising uses is in communication. Right now, every message you send online travels through light, whether in fiber optic cables or via satellite signals. But there's a limit to how much information we can send with ordinary light. By giving light a twist, scientists can encode extra layers of information into each beam, multiplying its capacity. It's like turning a single-lane road into a multi-lane highway, without laying down a single extra mile of pavement. Then there's microscopy, the science of seeing the invisible. Twisted light can help create sharper images at the microscopic scale. By shaping the beam, researchers can pick out details that would be hidden with standard light, pushing the boundaries of what we can observe in cells, viruses, and even individual molecules. Another remarkable application is optical tweezers. These are tools that use beams of light to trap and move tiny objects. With twisted light, scientists can not only push or pull microscopic particles, but also rotate them, just like turning a screw. This opens up new ways to study biological systems or build microscopic machines. And yet, the part that sparks the most curiosity, ISNT, what we can do in the lab, what might already be happening in the universe. If nature can twist light, then beams arriving from deep space could carry hidden structures, clues about the forces and environments they pass through. Imagine a signal from a distant star arriving here on Earth. To the naked eye, it's just light, but with the right instruments, we might discover it's twisted in a specific way, holding information about the star's magnetic field, the matter it passed through, or even the spin of a black hole. It's a possibility that pushes astronomy into new territory. Of course, there's a challenge. Twisted light can be fragile over long distances. As it travels through air, dust, or space, its structure can distort. Detecting and decoding it requires precision instruments and careful analysis. That's why this field is still young. Scientists are building the tools to read these patterns clearly. But the payoff could be huge. From faster internet to more detailed images of the microscopic world, from manipulating matter without touching it to uncovering cosmic secrets. Twisted light could become one of the most powerful tools we've ever discovered. And it all comes from looking at something as ordinary as light and asking, what if it could do more? In the next chapter, we'll leave the lab and follow this idea to the farthest edge of the universe where twisted light might already be telling a story we only just learned to listen for. Chapter 4. Twisted light at the edge of the universe. If twisted light is fascinating in the lab, it's even more intriguing when we imagine it traveling across the universe. Out there, beyond our atmosphere, light isn't just moving in straight, calm paths. It's passing through vast magnetic fields, bending around massive objects, and crossing clouds of gas and dust that stretch for light. Every one of those encounters can change the light's shape. This is where the mystery begins. Could some of those cosmic forces twist light naturally? If so, then beams of starlight or signals from distant galaxies might be carrying hidden spirals, like fingerprints of the journey they've taken. Black holes are a prime candidate for this. Their immense gravity can bend and distort light in dramatic ways. If a beam passes close enough, the warping of space itself could impart a twist and orbital motion to the photons. Detecting that twist could give us clues about the black hole's rotation, its environment, or even the structure of space around it. Then there are neutron stars, dense remnants of massive stars, often with magnetic fields trillions of times stronger than Earth's. Such intense fields could twist light in unique patterns, turning it into a messenger of extreme physics. Astronomers are starting to consider how twisted light might be used in space telescopes. Imagine pointing a future observatory at an exoplanet star and not only detecting its light, but also reading the hidden twists within it. Those twists could reveal whether the planet's atmosphere contains certain gases, or whether it's surrounded by powerful magnetic storms. This kind of observation would be like adding a new sense to astronomy. For centuries, we've studied light's color, brightness, and spectrum to learn about the cosmos. Twisted light could be the next dimension, an entirely new property to measure, one that could carry information we've been blind to until now. But there's a challenge. Cosmic light has been traveling for millions, or even billions of years. Along the way, it may be scattered, absorbed, or distorted. To detect a twist at the end of that journey, our instruments must be extraordinarily sensitive. That's why researchers are now experimenting with new detectors and algorithms to spot even the faintest signs of orbital angular momentum in light from space. If we succeed, twisted light could open a new chapter in our exploration of the universe. It might help us map magnetic fields between galaxies, study the most extreme objects in the cosmos, and perhaps even detect signals that don't fit any natural explanation. And that leads to a question we can't yet answer. If a twisted beam of light reached us, carrying a pattern that seemed deliberate, what would we do? In the final chapter, we'll look at where this research is heading, what obstacles remain, and why twisted light might be a key to unlocking discoveries we can't yet imagine. Chapter 5: A Signal in the Noise. Now imagine the final scene of this vast investigation. The years have passed. Every dataset has been examined, every error checked, every possibility debated in hushed rooms filled with chalkboards and glowing monitors. And yet, the signal remains. It is faint, yes, but it is also stubborn. It has outlived every test meant to dismiss it, and that alone makes it impossible to ignore. For the scientists closest to the work, the mystery is now part of their daily lives. Some treat it as an unsolved puzzle, something that will eventually yield to better tools and sharper theories. Others have begun to think of it as a shadow from somewhere we cannot yet see, a fingerprint from a part of the universe beyond our reach. Whatever it is, it now occupies a permanent place in their minds. You might wonder, does the public know the full story? Not exactly. The published papers describe the technical findings, the statistical methods, the graphs and numbers. But between the lines is a quiet admission, the sense that we have brushed against something bigger than our current science can hold. In the quiet of a late-night lab, with only the hum of equipment for company, you can imagine one researcher staring at the screen, watching the numbers change. Somewhere in those tiny fluctuations, hidden among the ordinary static of space, is a rhythm that doesn't belong. It might be a coincidence. It might be a natural process we haven't catalogued yet. Or it could be something that forces us to rewrite our understanding of reality itself. And here's the real question. If we ever did discover that the signal came from something intelligent, something not of Earth, would we even know what it was trying to say? Our entire history shows that meaning is hard to decode, even among our own species. Across the gulf of light years, meaning may be something else entirely. For now, the signal is still there, waiting. Technology will improve. New telescopes will rise. Algorithms will grow sharper. Perhaps one day we'll trace it back to its source and know for certain. Until then, the mystery hums quietly in the background of our knowledge, a reminder that the universe is not fully mapped, that there are still corners left in shadow. If you've stayed with me through this journey, you've rejoined a small group of people who looked directly at the unknown and kept looking. Maybe that's the first step toward understanding, not certainty, but curiosity that refuses to die. And if you want to keep exploring mysteries like this, subscribe to the channel. Leave a comment with your thoughts on what the signal might be, and share this with someone who would wonder too. After all, The search is never just for answers, it's for the next question.